Okay, Matt, just quickly going over this question for you. Right, a train travels along a straight track, passing point A at time t equals 0, and passing point B 40 seconds later. Its distance from A at time t seconds is given by this formula, this distance formula. Find the distance A to B. So what we've got going on here is a situation where you've got A here, B here. It was first observed here doing a certain speed, and it was noted at 0 seconds, and it took 40 seconds to get down to this stage just here, and that's all we know about it. So all I've got to do now is put 40 into there to get the distance that's down there. So that's part A. So let t equal 40, and that'll give us the distance from A to B using the formula. S equals 25 lots of 40 minus 0.2 lots of 40 squared. Working that out gives us, the calculator comes up, we got brackets 25 times 40, guys, getting bad and I can't bother that in my head, minus brackets 0.2 multiplied by 40 squared, and that's also outrageous, equals 680. So we've got 680 meters is the distance between both of these. It then says show that the train travels with constant acceleration. So we're going to work out the acceleration of the train by differentiating twice. So I get ds by dt, so differentiating with respect to t, and we get 25, ds by dt is your velocity, which is equal to 25 minus 2 times that is 0.4 t. And then differentiate again, and I'd say this, differentiate again with respect to t, and you end up with d2s by dt squared, which is equal to acceleration, which is equal to minus 0.4 meters per second squared, therefore constant. Okay, right, a bird passes point B at time 0, so the same time that this is passing here, the bird passing point B at an initial velocity towards A of 7 meters per second, so it's going towards there at 7, and flies in a straight line towards A with a constant acceleration. So we've got constant acceleration going that way by the bird of 0.6 meters per second squared, and an acceleration going in that direction of the train by decelerating in that direction at a rate of minus 0.4. Now, because we've got constant accelerations, we can now go ahead and you do the train first of all, and just use suvat. So suvat, and going that way we'll say is positive. Now it says find the distance from A at which the bird is directly above the train, in other words where they collide. So we're going to have to work out the collision point, or it's not collision point, where they both meet at the same time. And the distance we're going to set as the unknown there. That distance is set as x, which means that distance that the bird has to have flown by, if this is 680 across there, is simply going to be 680 take away x. So we've got u for the train. Well, we don't know what that is, so I can quite easily put it in here. I suppose across here I can say at t equals 0, I can use this equation here. V is simply equal to 25. So I know that the u there initially is 25. So I've got u in a positive sense going to the right is 25. I've got my acceleration going to the right is negative 0.4. My distance, my s, will be travelled an x, and there'll be at time t to be at that stage there. So using s equals ut plus a half at squared, shoving into there, I end up with x is equal to ut, that's 25t, plus a half a, well that's going to be minus 0.2 t squared. That's my first of me sim equations. Okay, I then look at the bird, so bird and we're going to use suvat again, but this time I want to say for the bird, I want to say just to make sure we get the signs right within this equation, I'm just going to say to the left is positive for this, because as soon as you've done that, it just becomes an equation or a formula. So it isn't dependent anymore on the signs. Sorry, of this direction. Okay, it's just a formula. So I can just change the way here, as I said before. So I've got u is equal to 7. I've got displacement is equal to 680 minus x. I've got my that's displacement. I've got my acceleration is equal to 0.6, and I've got my time is equal to t. So again, s equals ut plus a half at squared. I end up with 680 minus x is equal to ut, that is 7t plus a half at squared, that's plus 0.3 t squared. And that's my second of my sim equations. So all I'm going to do now is substitute that into there to find the time it is, because it's a lot easier to do that than solving for t. So therefore I end up with 680, take away, don't forget the brackets because it's going to change the signs of everything here, that is 25t, and I think it says minus 0.2 minus 0.2 t squared is equal to 7t plus 0.3 t squared. So expanding this out, and it looks like it's all going to have to go on to this side, because that gives you a positive, becomes a negative over here. So over here I'm going to end up with 0.1 t squared. I end up with negative 25t, comes over to make a positive, and added to that gives you 32t. I end up with 680, comes over to make minus 680, and that is all equal to 0. So solving the quadratic equation for t using the calculator or the quadratic formula, I'm just about to use the calculator. Okay, my white calculator, I can't do it on the computer. So I end up with changing the thingamajig, going down. Right, it's a polynomial of degree 2. It is 0.1 equals 32 equals and negative 68. I'm getting quite lazy. In the old days I'd have tried to solve that. Negative 68, press equals, and it works out quite nice, so I should have done it, just getting too lazy. 20 seconds, and the other one is minus 340 seconds, so minus 340 seconds. Okay, so impossible, or write the word impossible and identify the correct time. So across here, to finish the question off, therefore I can simply, and it'd be better to use this one, the distance from x, which a, which is x, is simply equal to 25 lots of 20 seconds minus 0.2 lots of 20 seconds squared. So working that out, and I'll get a distance of, so I can do it on this calculator now, I see that brackets 25 times by 20, close brackets, minus brackets 0.2 times by, I've got to write 400 there, it's embarrassing, blah, equals, so it's 420 meters from A, and that is how to do the question. All right.